Yeah, give him the bell again. I'll hit it harder next time. Okay, we're going to get started again. Next up, we have Greg Dunn. That's going to talk about some new type of onboard scheduling techniques called autonomous activity sequences.
All right. So, or was I on before? Okay. I'm Greg Dunn. I work here at Southwest Research, building next door. So this is activity sequences. Typically, we have a very simple operation for our instruments that we build. For mass specs and the Europa Clipper mission, we have a little more complex operations, so we've developed a new kind of scheduling system that we use within the instrument. Quick outline, there'll be an overview, a motivation of why we're not doing what we usually do, a little bit about the design of the sequences, and some sample timelines. I will preface this by saying right now it's a design concept. We haven't actually implemented this, but it's what we're planning to do for mass specs. Real quick, just on what mass specs and Clipper are. Dr. Birch yesterday mentioned some of the projects we have in work here. So one of them, Europa Clipper, is being run out of JPL. It's going to go to Jupiter and inspect Europa. And then one of our instruments on that is mass specs, which is, as Dr. Birch mentioned yesterday, it's the highest resolution mass spectrometer that's been flown in space or will be flown in space. Here's kind of an orbit in the life of Clipper with a mass spec centric view how we operate. Let's see if I remember where the pointer is. You've got Jupiter here with Europa going around it, and then our Clipper's orbit coincides with Europa each time around. Mass specs during the flyby here, we do some real-time data acquisition, but we also capture a gas sample essentially. That when we come way out here and we're away from Jupiter and all the noise, radiation noise, and we have a lot more time, we run that sample through our system. And so we've done that collection, and then when we're ready for the next orbit, we have to evict all that gas. So we have a pump down, a decontamination phase. And then coming into the orbit, we have to turn on, configure for science, bring up high voltage power supplies, tune our instrument. We're very sensitive to temperature changes and even some parts changes as they age. So we have an onboard tuning concept that gives us a nice tight peaks. And then here's where we're actually taking data. In run is about 2 hours. Closest approach, I think, is 10 minutes or so. And then we have 2 hour outrun. So on the in-run and outrun, we're taking low rate data. It's just decimated more. And on the closest approach, we're taking a higher rate data and also capturing that gas sample for the analysis out here. After the flyby data collection's done, we turn down the instrument, ramp down power supplies, do some analysis, and send summary data products. We come out here, and I already mentioned we turn on and power up, and then we do our more detailed analysis of that captured sample, and then we do it all again. So the activity sequences we're using to schedule all those activities, we're looking for an onboard schedule. It's an onboard scheduling mechanism to automate kind of that whole sequence of what needs to happen. It gives us a flexible schedule so that part of it I'll touch on is this helps with autonomy or with anomaly recovery, in that if we missed when an activity should have happened, we can slide it in time and execute it later if we need to, so that we can ensure there are some operations that affect our quality that if we had to we could skip. We get less data quality, but we could skip it to make sure we catch the flyby data. So the motivation, again, I've kind of touched on. We need more flexible operations than what we traditionally do. We usually have kind of a fixed time sequence. We need a robust recovery mechanism. Chad's presentation yesterday, when he talked about science instruments versus spacecraft, a lot of times a science instrument will fail safe. If there's a failure, we just come up and we don't do anything. We say, hey, I need help, and wait for ground intervention. We have a limited number of flybys, so we really don't want to do that on this one. If we have an anomaly, we want to try to reconfigure the instrument and take data. And then also prioritize activities. If we do end up slotting things, there are certain things we can skip and certain things we can't skip. So the ways we traditionally will run an instrument, if we have a really dirt simple instrument, it can be a hard code sequence. You turn us on and we just start turning data. Of course, with that, you can't do any complex timelines or varying things. Absolute time sequences, if I get the right button, store commands that are at a specific time tag time. If you reset or something happens after you've executed a command, there's really no mechanism to go back and re-execute your sequence. Relative time sequences are, it's a list of commands with a delta between them. So you kick it off at a specific time, but then the commands within it are relative. A little more flexible than the absolute time, but it's still difficult to resume one in the middle. Or if you have non-deterministic steps, we have a pump down step that we can model and say it should take 30 minutes, but it might take 25, it might take 35. So you can't really put a fixed time delay in there for something like that. And then for anomaly recovery, again, either fail safe, wait for operator intervention, or recover to just a default basic mode. Again, that doesn't really support the complexity of all of the activities we need to do from mass specs to configure and operate the instrument. So to get a little bit of it, so that's the why, and then here's what our activity sequences actually are. The design goals, we want to automate as much as possible, so we don't need, we need as little as possible commanding from the spacecraft. The spacecraft essentially uploads the sequence and says activate it, and we can be autonomous for the rest of the orbit. Lets us do the non-deterministic activities. This is a big one. Keep the nominal recovery as similar as possible. If we reboot in the middle of a sequence, there's running the sequence is really no different than if we turned on for the first time and we're running the sequence. We reboot and we just say, okay, run the sequence. Where are we? And that keeps it so that we don't have a whole separate logic branch for recovering from a reset. Robust recovery, and it will also, I've got some timelines later that kind of show this. It allows us to, in the event of an anomaly, we have to decide this ahead of time, but we can decide whether we want to give up some of our flyby time to make sure we have a good configuration, or allow for a less than optimal configuration, but maximize our data return. So for the terminology I use for the scheduler, it's, if you're familiar with project schedule, there's some similar terms. You've got the earliest start of when an activity can or should start, the latest time it can start, so that it has time to finish before it must be complete. And the latest finish is the time that's the cutoff. If the activity is not done by this time, you cut it off and move on to the next thing. With scheduling, there's also a earliest finish concept, but we're not using that in this scheduler. And then a schedule region is essentially that time between your earliest start and your latest finish where the activity is allowed to run. So it's a flexible timeline where steps will run as early as possible, but again, they can slide if the previous activity takes longer than expected, or if you had a reset or you're starting late for some reason. And if you miss the schedule region for a step, by the time you reach step 3, you've already missed its latest finish. You just skip it, move on to the next thing. So here's a sample timeline for the nominal case. All is going well. We get turned on at the right time. We don't reset. Everything's working the way we think it should. And this is focusing on that flyby region. So this first row, power on science prep, is really this first bullet here. We bring up our power supplies, warm up the instrument, configure our data processing acquisition FPGA. And the diagram here, the light bands, the lighter colored bands are when the activity is actually happening. The darker colored longer bands are when it's allowed to run. So you can see the power on is allowed to run clear out to here, because if we get power cycled here for some reason, if we don't run this step, we're not going to do anything. So it has to be allowed to run all the way out to the end. Our calibration and tuning phase, which is in here, you can see it's allowed to run a little bit into the in-run, but if it's not done by this point, we say don't, terminate tuning and just take data that we can. After we calibrate, we actually inject a gas to calibrate on, and so we have to get rid of that gas. So there's a pump down phase, which, again, if everything's running correctly and on time, it should end about there. But if it doesn't, it's actually allowed to run out to here if it's taking longer to pump down or something like that. In-run, close to approach, outrun, they don't have any extra dark bands because they're tied to the physics of we're passing Europa right now, so that those times aren't really flexible. It's here or nothing. And then after the outrun, we have our shutdown phase. And here's essentially, for configuring that, it's essentially a spreadsheet where you have the steps that are going to happen. Some kind of time reference. CA here means closest approach, so that sometime during the prior orbit, we would get a command that says closest approach is at this time, and then we can set all these steps up. Our earliest start, latest finish are all offsets from that reference, and we can support multiple references if we wanted to have an apogee reference, for when we're out at the other end, we could reference off of that. So when a step is, it's time for a step to run, we have a setup RTS, real-time sequence. So that's where we are kind of using our old scheduling concept where we just normally use just an RTS. But when it's time for the step to run, we would run that sequence, which does all the commands involved with that particular step. And when the activity's finished, there's a teardown sequence that puts the instrument kind of back into a baseline mode that any of the other steps could start from. Next. So the RTS, as I mentioned previously, it's usually just a list of commands with delays between them. On mass specs, we have a few non-deterministic things. The pump down can be. Our tuning process can be a little non-deterministic. Not wildly, but it's not a fixed 30-second thing. So we'll be expanding our RTS engine a little bit with some conditionals where normally you'd say, do this command, wait 5 seconds, do that command, wait 5 seconds. And we hit this line, and it can say, wait until, turn on the pump, wait until the pressure is below some threshold, or start the tuning process and wait until the tuning process meets a certain quality factor. And also an abort if we're monitoring temperatures, pressures, or something, and something is out of tolerance, we can say just abort the entire sequence in line there. A little flow chart just to show kind of how it's all running. There's just a 1 hertz tick, so this loop just runs at 1 hertz. For each step, each row is a step. Simply say, has it already executed or not? If it hasn't executed and I am in the schedule region, which is anywhere in the dark band, start running it. Just run its associated RTS. If it is running and its RTS is completed, we run down the teardown RTS and move on to the next thing. If the teardown RTS is running, just wait until it's done, and once it finishes, that step is complete. So the next time through the loop, we would skip that step and move on to the next step. So it just constantly runs down each step and says, what should I be doing right now? And this is part of what helps with the reset recovery, is that I don't really care that I just reset. It's just what should I be doing right now? Given where I am in the orbit, what time it is, what I've already done, what should I be doing right now? So for this is the one place where it's a little different on reset recovery. So we do have to know whether it was a CPU reset or a power on reset, because for a CPU reset, our hardware, for the most part, our high voltage power supplies will still be up. It was just the processor that reset. So we can just continue. If we were on step 3, we can just go right back to step 3. If it's a power on reset, we've lost all of our power supplies. We've lost our FPGA configuration. So we need to go back to step 1. But once we decide to go back to step 1, all of the other processing is the same. Here's another example timeline that shows an instrument power on reset. So, presumably we had turned on back here and started doing things, but we got power, the spacecraft turned off all the payload for some reason, and we got turned on at some other time. So this configuration, and again, essentially the dark bands are what get configured in the spreadsheet. So after a power on reset, we would come in and say, oh, I have to do this. Once that finishes, I'm still in the schedule region for CalTune. I can do that. When that finishes, the pump down step is next, but I'm already outside of its schedule region. So, for this particular timeline, when we configured this, we said, well, we'll allow pump down to run a little bit into the in-run, but if we're clear out here and pump down hasn't happened, just skip it. It'll affect our data quality, but at least we'll get data instead of spending the whole flyby pumping out calibration samples. And then, and then here we're basically caught up with where we should be in our timeline, and everything else runs as expected. And though the CPU reset is similar, except if I reset here at T2, I don't need to go all the way back to the beginning because all my power supplies are still up. I can just jump right back in. So if we reset here in the middle of CalTune, the tuning process itself isn't designed to be restartable in the middle, so it would restart. We'd start from the beginning of the tuning process, which makes it run, makes it finish a little later than the nominal timeline would have it finish. And then everything else automatically slides over. The pump down automatically slides out. Automatically, the in-run, when we start in-run, automatically slides out, and then everything else is caught up from there. So I mentioned a little bit ago, we have a kind of a quality-quantity trade-off. If there is a fault, and some of those timelines kind of touched on it, we can either decide to skip, say, the pump down or the calibration tuning. If we skip the tuning phase, it affects our data quality. We're not we don't have as tight of peaks, but we get more data. We get our data for the entire flyby. The other option is to say, well, if we don't tune, the data is worthless. So we have to do tuning even if we miss the entire in-run. So you can allow the tuning process to run as long as you want. Or you can do something in between where you're willing to give up, say, half of your in-run or your entire in-run, but when you get to the closest approach, it's, you're taking data regardless of the configuration. So sample timelines for those two cases. Here, we powered on late or power on reset, had a power on reset. We allow the pump down to eat into the in-run, but at this point, even if it's not pumped down, we say stop and start taking data. And on this one, this is the case where we say, okay, calibration and tuning is really important. We'll allow that to slide all the way over to where it consumes the entire in-run, but when we get to the closest approach, we're going to stop and use the current configuration. And some additional sample timelines for other configurations. If the pump down just takes longer than expected, so it started on time, but for some reason it's running long, again, it's allowed to run all the way out to here, and we have this latest finish that says, nope, you're done. That's it. Quantity over quality says when we get to the in-run, even if we completely miss calibration and tune and pump down, as soon as we start the in-run, the flyby in-run, stop all other activities and start taking data. Again, quantity over quality. We're not optimally tuned, but we want all of that flyby data. And then the other option is quality over quantity. Say we really want to have a good calibration and we really want to have all of that calibration gas pumped out. We could allow it to miss almost the entire flyby and just collect a little bit of data at the end. The schedule regions, the dark bands, those are, we configure that on the ground. So we make all these decisions on the ground as far as what our trade-offs are. And once you upload that, the dark bands here are static. So it's not dynamically making these quantity-quality decisions. It's something you upload ahead of time. On this particular orbit, we're willing to push the pump down out, or on this particular orbit, we really want all of that in-run data. And I think that was my last slide. Yeah. Any questions?
Okay. So you had mentioned time, the close approach, and perhaps Apogee as dependencies on the spacecraft data to understand what to do. Are there any others? Power, attitude, anything like that?
So we had
on that?
we actually met with mission operations. They're kind of doing a tour and meeting with all the teams. So that was one of their concerns, is this could be configured to basically allow MassSpecs to do whatever it wants, whenever it wants, which when they're looking at power with other instruments being on, there are some concerns there. So we do have to work with the overall operations concept for the spacecraft to make sure that as we schedule these, the pump down, we have an ion pump on board that consumes power. So they may say you can only run your pump in some window back here. And so if that's the case, then we would define this, this dark green band to just the window where we're really allowed to run the pump.
So that's still ahead of time, the dark band part, it's not going to dynamically.
The dark band is static. Once we upload it, and we intend to, for the most part, once we have the schedule down, we shouldn't be changing the schedule. But especially on the first couple orbits, as everybody's kind of feeling out how their instrument works and what Jupiter really looks like, we may be tuning that. Again, the different parts have to be negotiated as to, we would love to be able to run our pump anytime. And this lets us do that, but it also lets us say, well, spacecraft says I can run my pump here, and so I could put my dark green band there, and again, that's a decision that's made ahead of time, where we can lock it down and say, it's here or bust.
There's two, I'm working on this too, so there's two aspects to it. One is the pre-planning, where they in ground analysis, they analyze how much power they're going to have at various points, and as Greg said, that gets factored into this static schedule. However, of course, if their predictions are wrong and they wind up with a lot less power than predicted, they can always send us a message and say, we're about to turn you off. We can't, we don't have power for you.
Yeah, if they turn us off, this all goes away.
So that's the fallback approach.
Pull the plug.
If their analysis is incorrect, then they just turn us off.
Right. And then so some of these steps, this power on, if we don't do that, we're not taking data. If our power supplies aren't up, we're not taking data. So that either has to be allowed to run basically any time, or we have to make the decision that says, well, if we reset here, we're just going to miss the flyby. And again, we'll have to negotiate that with the spacecraft and the other teams. Calibration tune and pump down, those are really for quality. So we could actually skip those. We could still get data. It wouldn't be as good of data as we want. But if they say, no, you can only do cal tune and pump down out here, well, we'll push them back to here, put the latest finish out here somewhere, and just live with the results of that.
So I'm working on a program looking at some of the similar kind of things. One of our ideas has been to look at, is always concerned, there's always a concern with power.
Mm-hmm.
Don't let the payload just kill everything else.
Just do whatever they want.
Right. I don't have a problem with that, but other people do apparently. So one of our thoughts has always been to look at the bus as a service, so that you could ask it, how much power are you willing to give me? And then I could evaluate things. Have you thought of that, or has anybody in the room thought of that? Or done anything along those lines?
At least on the Mass Specs team, I don't think we've considered that. That's power is just something that's kind of bestowed upon. There's some negotiation there, but as far as that dynamically asking for power, that's not something that I'm aware of that there's been any discussion for Clipper. Have you heard anything?
No, I don't think so. I mean, there's been some outside of that, some kind of thoughts along the same line about finding out what resources are available and then adapting to that. But that's not, like Greg said, it's not the approach we're taking.
That's not something people have done a lot of. So, all right.
I do like that idea. It lets you be more. We could make this a little more dynamic and
right. You could trade that off and say, well, I could still get this one done.
Right.
And I can throw out these other that aren't as high a priority or whatever. Yeah. Thank you.
Other questions?
Anything else? All right. Thank you.
Okay. Thank you.